Welcome to our channel. This is the first video from our collection High School Calculus Selected Exercises. We want to solve the functional inequality shown on the screen, where f is a continuous real function of a real variable. Using the inequality that holds for positive values of f, bringing everything to the left side and forming a square, we find that fx is x over 2. From this equation, we additionally observe that f takes positive values for positive x. Using the inequality that holds when f is non-positive, we find that the value of fx must make the quadratic y squared minus y less than or equal to 0. From the sign of the quadratic, we also deduce that fx is greater than or equal to 0. And combining this with the fact that we are in the case where fx is less than or equal to 0, it follows that f must be 0 in this case. Therefore, we arrive at the following conclusion for the value of f at x. If f is positive, then its value at x is x over 2, and in the case where f is not positive, its value at x will be 0. We observe that the zero function trivially satisfies this property and constitutes the obvious solution to the given inequality. We will now seek non-trivial solutions that have the same property if they exist. We assume that there is a real number alpha for which f does not vanish. Based on the formula we found, alpha must be a positive number and f alpha must be equal to alpha over 2. We now consider a real number beta and distinguish cases. First case, if beta is less than or equal to 0, then the above formula gives f beta equals 0. Second case, if beta is between 0 and alpha, we observe from the formula that the value of f at an x belonging to the closed interval with endpoints beta and alpha either equals 0 or lies in the closed interval with endpoints beta over 2 and alpha over 2, which does not contain 0. In other words, the value of f will be located at one of the red points in the last diagram shown on the screen. If we denote by I the set of values of f at a closed interval with endpoints beta and alpha, since f is continuous, the set of values I must also be an interval. Since there is no interval lying within the red region of the last diagram and containing both 0 and alpha over 2, it must be that f at beta is different from 0. So f beta equals beta over 2. The third case remains, when beta is greater than alpha. Working in the same way as in the previous case, we find that f beta equals beta over 2. Thus, we conclude that the non-trivial solution of the given inequality is fx equals x over 2 when x is positive, and fx equals 0 when x is a non-positive number. At this point, the exercise is complete. Thank you for watching.